A warm welcome from me and from Design++ to our Autumn Lecture Series 2023. Today we are lucky to actually have Professor Kathrin Dörfler, and we are also lucky to have Professor Katharina Klemt-Albert here, so we actually have two lecturers today. And I'm very, very excited. It's the third lecture series. If you missed any of the other ones, we have a YouTube channel. You can rewatch all our lectures, but also other presentations that we have within the Design++ network. I'm standing here alone, but of course we're a big team organizing this lecture series. Vera Balmer is here, first row. Daniel Griego is here, and Michael Kraus. And together we organize this seminar series to bring a bit all the different departments together, talking about architecture, engineering, and construction. And now I'm very, very happy to introduce Professor Kathrin Dörfler. For the ones of you who never met her, she actually used to work here. She used to work at Grammatikola Research. She used to be my postdoc and long-term collaborator. Kathrin Dörfler is an architect, researcher, and educator in computational design and robotic fabrication, and holds a master's degree in architecture from TU Vienna and a PhD from ETH Zurich at Grammatikola Research. Her doctoral thesis, conducted at Grammatikola Research, was part of the NCCR Digital Fabrication Advanced Methods for the Use of Construction Robots directly on building sites. In 2019, Kathrin assumed the role of a tenure-track professor at the School of Engineering and Design at the Technical University of Munich. Here she leads a research group for digital fabrication in the Department of Architecture, exploring the synergy between computational design and robotic fabrication. The group's focus includes collaborative fabrication processes, on-site robotics, and fabrication-aware design for a sustainable future of construction. And today her talk will be on collaborative construction, and I'm very excited to welcome you. Thank you, Kathrin.
Thank you, Daniela, for the nice introduction. I welcome you all to my talk, which gave the title Collaborative Construction. I see many familiar faces here, and I'm giving the presentation today in my role as Professor for Digital Fabrication at Technical University of Munich, and as co-spokesperson of the Collaborative Research Center, which I am co-coordinating since 4 years. Since 2 years actually, but since 4 years as a member. Additive manufacturing and construction, the challenge of large scale, so a lot of 3D printing, which I will present today. So as you all know, digital technology is a powerful tool for managing complex systems. And in particular, if we compare the construction sector, or it is often compared to other types of manufacturing industries, most and foremost the automotive sector or retail product sector, often it is said that we see that the production chain from design to final assembly is largely automated today, in contrast to construction. However, we believe that construction is not directly comparable to the manufacturing industries or the classical manufacturing industries. The built environment is intertwined with the material reality of the society, the geographic location to which it belongs, and it is a product of mostly its legal framework conditions, its regional availability and the supply chains, and also the industrial practices, skills, and technologies that are associated with it. So to enable a sustainable change in the construction industry, we need novel systemic approaches and also transformative technologies that come within the construction logics to become better and more sustainable. So against this backdrop, this presentation and the work with my team advocates for this sort of holistic approach, emphasizing the need for digital construction that is somewhat robust and can withstand uncertainties, is to some sense also redundant and resilient to adapt to changing conditions, What I mean with this, I think it's best explained on behalf of a series of case studies, experimentations, and explorations. There will be 6 of them, so please be a bit patient. I will try to be in time. So the first project that I would like to talk about today is called LOCS. LOCS stands for Interlocking, Collective AR-Assisted Assembly of Topologically Interlocking Structures. It was one of the first projects that we did at Technical University of Munich. And the research was around whether and how a team of people can participate in the assembly of a pavilion using only mobile AR technology. Following customized user-specific constructions visualized on a mobile phone. In this setup, the building instructions can be retrieved by multiple users via a mobile AR app that positions user-specific building instructions 3D space, custom to the user in question. And the research question revolves around how multiple participants or users can be synchronized and coordinated over a cloud, and how participants can intuitively log in, participate, and log out at any time of the process. For this, we developed a material system consisting of these discrete wooden blocks that offer form-fitting connections, and it makes it possible to use these units both as building blocks as structural members, but also as sort of temporary support to build up the structure and then remove it again once the structure reaches sufficient stability. All of this is stored in an assembly information model, a graph data structure, where each of these blocks is represented by a node of the structure, but also by the topology, basically representing all the dependencies of these building blocks and the actually no sequences, but just dependencies. And this allows to continuously compute the states of other nodes according to the currently assigned states. I will explain this in a bit more detail. So we built up this pavilion in the front of the Pinakothek, which is opposite to Munich. In Munich, this was during COVID time, so everything had to be sort of closed up. And you can see here the user interface, so it's all running on Unity on a mobile phone. And basically we had 4 of these phones, and each phone was used by a pair of students, so always 2 students that would work together. And one that is basically holding the phone and talking to the other student, basically reading the instructions. You can see here that we use some sort of color coding, resembling whether a element can be built or should be built, whether one of it is selected by another participating user, or if it's removable, meaning that it can be removed again. And by this, we kind of built up this pavilion sort of in a sort of installation for this Kunstareal festival, and this is just the remaining building. The module itself is, of course, reusable, so there are no mechanical connectors, so we took it apart and rebuilt it at the Innenhof of our professorship. Yeah. So these are some images from the installation. And this work was sort of a little bit, I mean, it's very simple, but it was still kind of showing some directions what it means if multiple agents can participate together. And we sort of try to expand this by bringing robots back into the system, no? So that we still work with mobile AR, but collaborating with collaborative robots. And this is a work that I have been developing with Daniela Mitterberger for a while already, and 2 of her MAS students this summer. Human-robot cooperative assembly of reconfigurable reciprocal frame structures. It aims to foster a collaborative ecosystems where humans and robots can complement each other, and tries to understand the sort of limitations, but also the opportunities in human-robot collaboration, highlighting that this has to be considered in design, but also during fabrication. Yeah. So we have seen research, exciting research that looked into multi-robot assembly and shows the effectiveness of collaboration among multiple agents, such that it is enabled that more can accomplish than with just one participating agent. And the question is if also humans become part of these processes, if even more could be enabled. For instance, that we can take advantage of human cognitive abilities, versatility, fine motor skills, plus the robot's precision and sort of endurance. What we think, this kind of logics or this sort of thinking also has to be reflected in the design of the building structure. So we have to think, how can we meaningfully distribute tasks between humans and robots? Like, what can everybody do best, so that they can support each other in the best way? So this has to be considered during design, and then during building, of course, we have to find a way how these two entities can communicate with each other. So the mobile phone is always for us a way to kind of visualize 3D data in 3D space at the correct time, at the correct place, let's say. And therefore allows to kind of have a shared digital space that both humans and robots can share. Again, in relation to this concept, we have basically developed some sort of assembly logics that would reflect basically, or that would allow to examine sort of this concept. And we have been building up on the basis of this reciprocal frame structure, where we always have models of 3 basically that kind of grow along a guiding surface. And during this growth algorithm, we already take into account, you can see here very lightly colored, the robot reachability, which kind of should ensure the fabricatability at each time, and the guiding surface, which is basically also guiding the growth algorithm, in fact. And with this, we design already with the constraints, meaning that the fabricatability is ensured at each step. So it's not a post-processing step, but it's actually part of the design generation. And also the structural stability in this case should be ensured at all times. Again, we work with this graph-based sort of storing method, where again the states, the geometry, the topology is stored in the model, and allows to basically store all the fabrication data that is necessary, and also whether it's built by a person, by a robot, and all the sort of data that is associated with it. And then Eleni and Joe joined by developing this nice AR interface. This was this summer, and I show you quickly a video that we tried to do, because always a bit always a bit difficult to communicate. So this is basically the overlay of the AR app, and here you can see how, I mean, you can hardly see, but basically you select an element that needs to be built, and then you can trigger from the mobile phone the calculation of a trajectory for placing a new rod. Then you can also visualize how this manipulation procedure is performed with this sliding you can see here. And then you can also trigger basically when the robot has to basically place the rod. Then once the robot has placed, then the person comes in and assembles the second rod. So it also kind of has to follow some logic. And while basically the first robot stabilizes the structure, the second robot comes in and continues. No? And then it's always like turn taking. Always the robot is basically also used as a temporary support, and then the second can continue. And you can see here also the interface. We have just worked with tags this time, so there's no object recognition. And and you can already see the limitations of this also. No? So we would actually require much more spatial awareness in order to really make this very fluid and intuitive. No? So the research, we have been doing it for a while, also with Daniela together, it really shows that if we don't have the best spatial awareness, we will always have limitations in really making this kind of shared workspace very, very intuitive and seamless. And now you can see when the robot lets go, structure shakes because it's also a bit soft. And then in theory, now the next rod could be assembled. No? Yeah. So here are just some images of the. What is nice is still that since the robot is collaborative, it really is used as a sort of smart drill. Yeah, it's really, since we are working with these tools, it becomes very kind of easy accessible to kind of perform such tasks together. And this is just like, I think Joe did the drawn imaging, yeah, exactly. Just to see a little bit also the scale. Again, this, I forgot to say that all the nodes are the same, so this structure is also completely reconfigurable, so we could disassemble it and assemble it again. So, but this topic of spatial awareness is kind of following us all the time. So we have now initiated a collaboration with Professor Stefan Leutenecker, machine learning and robotics, to really start to more fundamentally go into this topic of spatial awareness to support on-site construction or to support mobile construction. So spatial AI, big name, but it refers basically to the artificial intelligence that focuses on the understanding and utilization of spatial information with high precision, enabling robot systems to comprehend and interact with the physical environment in a manner that mimics human spatial awareness, not to have a semantic, but also a geometric understanding. And one of the materials that repeats itself, I forgot to say that what this allows is to work not just with new construction, but also in existing contexts. No? And one of the materials that is very apt for reuse is our beloved brick, because until to the 1970s, when no cement was added to the mortar due to the weaker nature of the mortar joint, it's very easy to take the very small scale model apart again. Therefore, bricks and stones were highly reusable, as also depicted in these examples. So when we look into circular material use, of course, we first want to reclaim the material, and then we want to reuse it in a circular way. And we have set up to start addressing this topic. Basically, we have now started with bricks, as we see it kind of accessible or easy to start with. For the mobile robotic disassembly of a brickwork structure. And we have set up a case study which with extremely simplified conditions, so no mortar, no no additional complexities, let's say. But the objective was to realize an autonomous process for the robotic disassembly of a manually assembled brick wall with no CAD geometry and no prior knowledge. No? And we have started to train models with synthetic bricks, so not real bricks, in a lot of different situations with a lot of different lighting conditions, such that both a full structure can be recognized, but also the individual objects within. And we've integrated this again into our mobile robot. And you can see here the camera, stereo vision, and then what the robot can actually see. And we have set up a two-step task management system. First, to kind of a search routine to kind of identify the workpiece in general, and then an iterative loop to kind of start to disassemble the whole system. And you can see this here. I mean, it's also not completely fluid yet, but because we take kind of single snapshots, and this is kind of the first search routine where the robot searches for the workpiece, and then the second one where we can identify basically the single bricks in the structure. They don't have any, they're not identified, so they're not tracked. They're just, every brick basically is identified in the image. And then we compare it to a digital model that we set up as the construction, or as the disassembly progresses. And then each brick in reach, or each detected object in reach, is basically then taken off. No? So you can see here that basically the digital model is generated as the disassembly progresses. And then basically the routine is always the same. The robot looks at the structure, it takes one of the detected bricks, if there are multiple, plans the trajectory for putting it back on the storage, which we have now put on the back of the robot, and then basically continues with this routine until no more kind of objects can be taken out. And you can see here the digital twin, and this would be the first patch that it would disassemble. And you can also see that it kind of goes in the opposite way as you would do when building it up. So kind of goes patch-wise with this kind of trapezoidal shapes down. Then we relocate the robot manually, so there's no autonomy in there, and we use a tag to put everything into the same workspace globally, because locally this information is not important. For the disassembly routine, actually this is not as important. So we go, in this case, 5 times to basically take this whole structure apart. And yeah, what is nice actually is that you create a digital model during the disassembly and you could basically reconstruct it in the same way, which is somehow nice. Of course, not super accurate to the extent that it would be required, but if we can tweak this, this would be a nice way how to think also into reconstruction again. You can see here the 5 patches. So while it's not super accurate, it's super robust somehow. So we had 100% task success rate with these 48 bricks and 5 times relocating. Here are some of the numbers that basically quantify a little bit of the cycle times and the post estimation of the single bricks. We would now need to measure it a bit more precisely to really make some better assumptions on the accuracy of what we can achieve. So while we are very invested, let's say, with developing these technologies, we are also very invested in working with architecture students and really bringing these technologies into the design sphere. And this is also very much connected to this additive manufacturing and construction cluster. We have initiated 2 pilot projects in the last 2 years where we have set up design studios where we work together with the students really on architectural design topics, and I will now talk a little bit about this, where the focus is on the design, not only in terms of what is built, but also how the whole process is performed, and of course also leveraging additive manufacturing technologies to some extent as a design driver in the system. And what we try to teach is that this is nothing new for you, but I still repeat it, but in the classical way, you design, then you engineer, and then you construct. And of course, we try to see this all in a coherent, sort of very early stage design to bring all of these topics together. And in infrastructural design, which we have looked a little bit into it, of course, these functions that we want to integrate, so is always related to form and force and the material or the production technology. You can see here a spanning structure for a pedestrian bridge that is first taking into account the mechanical properties of the material, and then in a second step, the limitations of the printing system, so that the form is then discretized into the parts such that they can be 3D printed. And in building construction, this goes far beyond form and force, but it includes also an extended functional hybridization. So we try to kind of integrate multiple functions. Do they relate to structural, thermal, climatic, building design requirements into the building components, all sort of enabled by the additive manufacturing or digital building fabrication technologies. 3 projects, I will browse through them quite fast. Hopefully. So the first one, Bridge the Gap, was a design studio that I did together with Pierluigi D'Acunto, professor for structural design, now 2 years ago, in which we aim to explore the integration of form, force, but then also the fabrication technology as a main design driver in the design process. And for this particular design, we focused on a method called selective paste intrusion. So this is a method where a cement-based, or actually any kind of binder, is intruded into a gravel bed, and then layer-wise you can build up a structure. These structures are not reinforced, so they are very brittle. And in particular, in this case, we used a lightweight aggregate, meaning that the mechanical properties of the material are quite weak. However, you can react to that, of course, with geometry, with geometric design. And knowing this, you can also take these features very early into the design thinking, in this case, to set up a model for sort of a compression dominant sort of load shape. And we have developed a method to kind of go sequentially, to kind of first have a very rough outline on the global geometry, then go detailed more into the segmentation and then into the final structural design. And we have been able to realize this also within the additive manufacturing AMC cluster as a one-to-one prototype. And this video guides you a little bit more through it also. Yeah, you can see here again the design method. So first, basically, because it's a sort of unreinforced system with post-tensioning cables, of course, but it takes into account that we want to go into the arch-like or shell-like shape. Then the mechanical properties need to be tested and then fed back to the material model. In this case, which type of aggregate you use is really defining also the mechanical properties of this. But we looked into taking a very weak material with a very low cement paste, but having it a bit more bulky so that we have more interface between the parts. So, so it of course follows the stress lines, and then this is not automated, so we did this all manually. But basically, it follows the stress lines and then kind of integrates the detailing or how these parts come together into the 3D printed parts. This is the post-tension cables, how they are routed basically through the structure. And then because we didn't want any lateral loads in the supports, also the cables that would put the two things that would kind of hold the supports together. This is the 3D printer. It's an industry partner in South Tyrol who have developed this printer together with TOOM, which is 6 by 3 by 2 meters, something like this. And the segments can be printed in one go, which is nice. And it's a very robust process because basically you can very easily remove the gravel bed afterwards. And then here you can see the not very smart way of assembling. A lot of support needed, but something that we would need to look into in a later stage. Yeah. And what is super nice is that you don't need any, so there's no mortar needed between the parts because it's so precise, and also the connections are form fit. Yeah. I have to wait for the credit slide. Of course, you can see here the associated researchers. So we work with the MPA, then the material science scientists, and also the people who developed the process at TOOM. While this very much looked into sort of the structural capacities of the system, when we look into really creating building components for it, then the climate functions are very important, or the insulating functions must be taken into account both for the indoor climate but also for the outdoor climate. And so we have started to look into building systems. In this case, the architectural reference of Marcel Breuer, a prefabricated facade systems from the 60s already, and a method for the design and manufacturing of this augmented with the possibilities of additive manufacturing. So in traditional industrial construction, we always have a load-bearing layer, an insulating layer, a sort of protection layer. And this is done, of course, to comply with the codes and to be able to react to all of the requirements that we have. This multi-layered nature, but also leads to that once we deconstruct the building, that it's very difficult to dismantle. Usually these layers are glued to each other, and when we think about this, we want to think about like kind of using as little materials as possible for doing that, and also not so many processes. This has already been thought out in this reference So this IBM Research Center in La Gaude in France aimed to unify building technology installations and passive solar protection measures in a single modular prefabricated facade component, but of course sort of limited with the production of casting techniques at the time. And in this case, we looked into SCA, selective cement activation technology, which is similar to the first one, but the bed is not gravel, the bed is like cement powder, and you activate it selectively with water. And I would say that it's much more high resolution, but it's of course also way more brittle. And it's not so easy to scale. No? So you will also see the limitations of this. So we try to develop also a design methodology to integrate both the insulating functions and the load-bearing functions into these prefabricated building components, where we made a hypothetical design, where you can see that we first basically parametrically adapt the size of the glazing area to the solar sort of situation of this circular building layout. Is a hypothetical design, not a real building. And concurrently design the internal structure to conform with the thermal insulation and also the sort of structural zone to conform with the structural requirements. And I will also play a quick video of this one. No, it doesn't seem to play. Quickly look. So this is again a one print bed endeavor. Now this is not discretized, it's really printed as one piece, so it's 3.8 meter high, so it's really large. And of course we had to sort of deal with all the cracking and the deformations that play into there. And also all the sort of the constraints of the fabrication system are also reflected in how the details are made. No? So these channels have to have a certain size because it's really difficult to take out the cement powder. So they are much larger than they actually would need to be. And also, since the material is less load-bearing than the process that I've shown before, we had to integrate it sort of as a stay-in-place formwork to then also put reinforcement and sort of cast parts of it for the structural zone. And then it's printed basically in a horizontal way. It's taken out and basically the powder has to be removed. And it's much more difficult than in the process that you saw before because the powder is more sticky and not so easy to take out. Then you can see here how basically the rest, these channels are filled with the reinforcement and the cast concrete. So it still doesn't really conform with what I said before, that you just use one material. No? So, and here you can see also little cracks. It's still sort of, it was still kind of a major achievement that we managed to realize this at that scale. Then again, here the reinforcement, the insulation material was kind of blown in from the side. And here the doctoral students took some measurements of the sort of surface temperature of the component. Yeah. And you can see here also some of the parts where sort of the cracks have taken over. Yeah. So we have to try it because we like the concept. In principle, we have now tried to go back to the other process and kind of rethink that kind of how can we stage us really with one material. And we have looked back into this selective base intrusion, starting from this concept that you really can construct a building really just with one process, one material, both for the wall elements and also for the ceiling elements, envisioning basically how the components could be prefabricated and then put together into one building without reinforcement, but maybe potentially again with post-tensioning methods. And this really draws, of course, the inspiration from this ancient stone masonry architecture, but with the ability to really have a hollow stone. No? So what is kind of inside these elements has all of the functions that I've been talking before. So the shape of these components first reacts to the size of the printer, then also to the statical requirements, so this sort of compression dominant load transfer, then also how these pieces are assembled. So if you assemble from top, you want to have this kind of segmentations line tilted also, and also such that they can interlock nicely so that you don't need any more mechanical connectors. And what is really nice about this, that it really goes very close to this Infraleichtbeton, so or Leichtlehm. So these two things are kind of in the same field. And the binder, whether this is like cement or any other binder, is basically the load-bearing component, and the particle itself is a lightweight aggregate, which is highly insulating, and you can imagine that if you selectively bind the material, that the particles which are trapped inside such closed cell geometries are remaining in the structure, both as a insulating component, but also, of course, with a little bit of a thermal mass. What we refer to as this trapped particle principle, you can then also see that the more you bind in the system, the more it carries, but the less you bind, the more it's insulating. So with that knowledge, we can kind of steer the internal geometry of these parts. And we have also now made the first prototype of this, which is like just a very small cutout, because we have just started this research, but with some kind of promising results. Yeah, here also the process of printing is detailed a bit better. So this binder is super liquid, and it goes into a print head that kind of makes droplets of materials, like a printer, like a Strahldrucker. You can see here that the flow behavior of the cement base is super liquid, because it has to intrude the material a little bit, and it also cannot harden so fast, so that it kind of doesn't give the cold chance. We know all of these issues. And then here you can see how the gravel is basically put into the aggregate container, and this agitation container that kind of steers the binder. And then just press print, like, which never works, but say so. And then you can see that how the gravel is basically distributed on the bed, layer-wise manufacturing the part. This is the small version of the bigger one that we saw before, the first prototype that we have in the material science lab. And then you can see also again how easy it is to, rock print, like it is to remove the gravel around it. Yeah, you can see here this was now the size that we have now firstly produced, and we are now in the process of also taking the sort of measurements to see if the simulation basically fits the assumptions. Yeah. And this is just a photograph of this kind of internal cell structure. Yeah. So with this, I thank you for your attention. If I probably you have not seen all of the credits, it's like really a big group behind, especially the last 3 projects. And you can find more information on the website AMC, and also on the website of our professorship. And now I'm happy to take questions if there are. Thank you.
Thank you, Kathrin. I will propose to put the questions to the end. Okay. So we put both questions together for both lecturers, and then also can after the next lecture make a smooth transition to drinks and apero that we have. I am very happy to introduce Professor Katharina Klemt-Albert. She's director of the ICOM, the Institute of Construction Management, Digital Engineering and Robotics in Construction at RWTH Aachen University. Before joining Aachen University, Klemt-Albert was chair and professor at Leibniz University in Hanover since 2016. Her academic career began with studies in civil engineering at Ruhr University in Bochum. In 2001, she earned a doctorate with honors from the Technical University of Darmstadt in cooperation with the Northwestern University, USA. Professor Klemt-Albert has extensive management and industrial experience. She spent 14 years in top management at Deutsche Bahn AG, most recently as managing director of an international engineering company with 1,500 employees. She was responsible for numerous mega projects with a focus on the Gulf region, Asia, and South America. She's also the founder of Albert Ing GmbH, a specialized provider for digital transformation. Hereby welcome you very with happiness, and I'm looking forward to hear your talk.
Well, thank you so much for the nice introduction. I'm very glad that I have the possibility to speak to you tonight, yes, and to follow up perhaps a little bit on Kathrin Dörfler, but I think I brought a little bit different perspective since I'm a civil engineer. So I would like to start. I want to talk about sustainable digitalization in infrastructure and construction and give you a small, perhaps also German perspective, what is going on, let's say from the governmental side in Germany, and how can we catch up from the research and scientific part. So what are the enemies of construction? So first of all, it's sustainability. So from construction part, we owe like 38% of the CO2 footprint. This is true for the construction itself, but also for maintaining our built environment. So this, of course, is a hard word, yeah? But on the other hand, we do have a huge possibility. So if we change something in construction, we will have a big impact also on the CO2 and also on the climate. So first, sustainability. So second, productivity. So if you look at the productivity, this is the statistics from Germany, but it's pretty the same also for the US, so it might be the same in Switzerland as well. So you can see the average line here is the gray line over the last 3 decades. So we did in productivity overall, like let's say 150% plus. But if we look at construction, so we are lucky if we are above 100%. So we are really, really low in productivity. So it's more like decreasing rather than increasing. So we have the certain amount of people, like for 3 decades at our construction sites. And it's not a nice work what can be done there, of course. And this is now combined with the problem which we have in all our, this doesn't work so nicely. This is combined now with the lack of workforces, which is of course very true for all of our industrial countries, but especially for the branches of, let's say, food, so restaurants and so on, and construction again. So with the lack of efficiency and combined the lack of workforces, we need to do something. And so I see these challenges here, lack in sustainability and efficiency and the lack of skilled personnel, plus, well, I know some projects which don't meet the time and budget goals at the end. Perhaps not your projects, but we all know some of them. So we need a solution for that. And I think digitalization is key. So we need a very consistent digitalization at this point. Otherwise, we won't cope and we can't face these challenges in construction. So if we look now what is going on, I promised to talk a little bit about Germany. How does Germany reach sustainable digitalization in buildings and also in infrastructure? So what are the initiatives, let's say from the governmental side here? So first of all, there are lots of master plans in charge at the moment. So these are a couple of them focusing on infrastructure, like traffic infrastructure. So you have a master plan, for example, for federal highways, and also one for road and bridge construction at the state level. This, for example, is from Bavaria. So they all say that for new projects, we have to implement building information modeling. I think you are aware with this. So for the new projects, where we start the new design, we will have at the end a building information model, so a digital model. So the same is true if we look at the federal level in Germany for, let's say, buildings. So for example, there's a master plan BIM for federal buildings. I know it quite well because I had the chance to write it. So I really suggested there that we set a goal to implement obligatory building information modeling. And this is already done now. But still, we do have most of our buildings are existing buildings. So if we start now to get, like with the new ones, building information models, we don't have them for the whole infrastructure at the moment. And it will, let's say, take years and decades to get for all the existing buildings there. So we need different solutions for that. Plus we have different, I'll say, challenges also with respect to affordable housing, for example, in Germany. So there's a governmental goal to build up 400,000 affordable housings every year. And we were thinking at a round table about that. How can we fulfill this? Because it should be affordable and it should be sustainable. And the approach here, for example, was to tenure a big framework agreement at a federal level. And there were 20 companies now getting this tendership there. So in every, let's say, every city and every commune in Germany can now take these tender proposition and get something like a serial and modular construction, so that we have a more scale effect for these affordable housings. I think there's something ongoing at this point. And we also have, of course, if we look at digitalization, we had last week, this is a picture from, no, this week actually, we had a big Digitalgipfel, so a really summit from the German government. I think half of the ministers, including Minister Scholz, were there. And we were discussing on how could we enhance and foster digitalization in Germany in general. And also I had a session on concerning construction industry. So there's lots of ongoing at the moment. But of course, I think we need to speed it up, that I would say in my own words at this point. So what I want to show you, I picked out some very specific examples to show you what are we doing specifically at some points to solve some of the questions which are there. So one of the questions is, how can we extend the lifespan of infrastructure? So the question is traffic infrastructure. So we have a huge challenge here in Germany. Sorry, this is in German, but we have 65 bridges in Germany. And we need to renovate 4,000 with respect to the highways. Oh no, it's working. With respect to the highways and with respect to the railways, we even need to renovate 9,000 bridges in the next, let's say, years. So it's a lot of capacity, which we know, and we don't have really the capacity in the construction industry to go for all the bridges. So it's more than we could go on for, let's say, reconstruction. This is one point. And the other point is we can't just take away all these bridges, because we need to have some mobility and logistics anyway. So it's a real problem. So if we could kind of enhance the lifespan of the infrastructure and use the bridges, some of them at least, let's say like 5 or 10 years longer, that would have a very sustainable impact, and that would cope with for us with the situation. So what do we need if we want to kind of enhance this lifespan? So we need, of course, at first, a digital twin of the infrastructure. So if we have the real building with geometry and with different, let's say, data, we could make a building information modeling of the existing structure. And then we could set up a monitoring system with condition and monitoring and so combine it. We call it structural health BIM. So we could use this model, this digital twin, combined with the data we are collecting from the existing infrastructure to really predict the, let's say, the health of the bridge. And then, of course, go there and do some very specific maintenance there and enhance the lifespan in this point. So, of course, we need the geometry. Well, that would be quite easy. We can do laser scanning. So there are some automation processes behind it. So it would be quite okay. But we need some more data than the geometry. We need material information. So which type of, let's say, construction did we do there? So we need some data. So what do we do today? So there are engineers sitting about lots and lots of paper and looking at these existing plans. So in these existing plans, they look like this. So it's horrible. They are digitalized, but they are like a PDF, so like a scan. So you can't see anything on it. So you can imagine how long it's time for the engineers to really collect the data out of that. So we said we would like to train artificial intelligence to collect the data out of these existing plans and combine it with the information which we get from the scans. So what we did in our project is called multi-data fusion. So we have the laser scan. We do it by drones and robots and so on. And then we have the existing plans evaluated from artificial intelligence. And then we combine it and put it together in a geometric model enhanced with the information, with the content data we get from the existing plans. And then we put it on a so-called common data environment to get all of the information for the bridge, for example. And then we can, of course, like have a bidirectional data exchange at this point from the digital twin, which we get with, let's say, monitoring systems, for example, from the bridge itself. So we have all the linking there. So we have a localization. You see on the top left here, localization of the sensor systems. And we get the monitoring data. Mostly, it's not really real time because we don't need like the every second, but it's like weekly data we can collect there. So we have the building data, and then we can combine it also with like damage reports and so on. So we will have, with this multi-data fusion, we really have the whole bridge on the common data environment and enhanced with all the, let's say, current structure and the current health of the bridge itself. And this data now goes to the predictive maintenance. So the one who is kind of doing the maintenance itself, he can have a look at the bridge, and then he can see if there are like traffic lights. If it's green, then everything is fine. So if it's yellow, he can look inside and really look at the data from the monitoring, for example. And if it's red, then he has to do something for the bridge. So in this case, we really can kind of optimize the process of maintenance and also use the bridge much longer than we could if we wouldn't do the monitoring at every site. So we're looking, this is already quite nice, this project. We're looking also a little bit further to do the inspection then on site, because also here we have a lack of personnel. So we have the structural inspector, we have the asset owner, so the one who is owning like the bridge, like the German railway, for example, and we have a manager of the maintenance, and we want to have them at different parts. So we don't want that everybody has to go out to the bridge. So the one who's doing like the maintenance specialist, the owner of the bridge, he should sit in his office, and there would be just one person at the site really looking at the bridge, and then perhaps another expert from another office. And what we are doing now with this digital model is like to really do an inspection of the bridge while just one person is on site. And so we have set up, this is still in the making, so my film is not as nice as the ones from you have seen before, but let me check. However, yes. So we have like a virtual environment here, and then the inspector can have a look at the bridge and gets like augmented reality, all the information, and then they can really talk about these informations in real time at the same time and get all the expert view there with just one person standing out on the bridge. So that's what we are currently working on. So next topic, how can we build with less CO2 output? And if we look at concrete, of course, concrete is a real problem, but on the other hand, it's very nice material. So it has convincing, let's say, strength and so on. And well, if we look at the concrete slabs, we usually build them like in the same thickness. Why do we do it? It's not necessary in terms of that we need the material from the structural side, but we don't manage to build it in a different way. So there are some, let's say, techniques to do it differently. For example, you could put there some plastic voids inside the concrete, which are filled with air. So you won't need the concrete at these points. So if you look at a slab, for example, then you have the calculation here, and you can see that here in the middle, you wouldn't need, or you would need, for example, at a column or so, you would need from the structural part, you would need the material. But further away from the slabs, you don't need the material. So if you put just here these voids into it, then you could reduce the whole concrete volume by 30%. And this is a nice thing, because if you reduce it by 30% in the upper floor, then of course the columns and floors beyond it, they would also have less material and need less strength. So you can really, over the whole building, you can reduce everything about. So this is a nice approach, but why isn't it done? It's even, we must say, cheaper than if we use the whole material there, because concrete is quite expensive. But the problem is that we don't have the people as for the assembly at this point. So these voids, they come in half parts, and you put them to the side, and you have to put them together to a whole holistic part. And this is done with manual workforce. And so this company who are building with these voids, they asked us, could we find something to do it to do the assembly process by robots here? So the idea is really to go with a robot to the construction site and to let it assemble these parts, and then to install these construction process at the site, and to get the reduction of concrete there. So the last example from my side is a completely different one. It's nothing to do with, let's say, realization and robotics, but it's how can we get citizens more involved in construction processes and in the construction projects. So we have the problem usually that if we have a new construction project, there are lots of people from the public who are, well, reluctant in the acceptance of these projects. And we have very long spans, how long until we get an acceptance for these projects. And there are some examples also that even when we got the acceptance, that at the end, when starting the construction part, then there was a lot of, let's say, resentments against these projects. So what we kind of set up at this point is to do the whole visualization concept digitalized. So we have the designers here, the planners with the building information method, and then we have a BIM model as a single source of truth, and we want to do like visualization and use this with an augmented reality also for the public to participate in the project. So we have several use cases defined at this point. So like a visual conceptualization, then a modular design, how can we approach with the modular design, and also a digital planning approval. So the whole approval process gets to be more digitalized at this point. So this project just started at our institute, but we see already that we have lots of interest, especially, let's say, from the federal highways and also from the German railway, because they say we have like processes, I don't know if you're aware, but in Germany it's like processes from 1 year or sometimes 2 years until we get this approval. And it's because we can't really involve the layman, because if we show them like design plans, they don't understand it. But if we visualize, then we have a really possibility to reach them a little bit clearer at this point. So the question what we are thinking about, of course, is how can we really reach construction, and how can we reach also construction industry? And this is, I would say, the goal of our institute, where we are looking at. So one is that we are focusing on infrastructure and also on building structures. And we try to enhance like circular construction and tackle it also with automation processes. But we are always looking at the digital transformation. So we can't do a digitalization and automation without the people. And well, construction industry is quite conservative at this point. So if we look at this digital transformation, I would say we start from an improvement in transparency and validity with building information modeling. So this is the first step. And I think we know where we want to land at the end. We want to go to, I say, rethink construction with circular construction, with individualized automation, value-oriented process design, and also people-centered collaboration. But this step, going from here to there, is very huge. We can't reach it in the next moment. So what shall we do? What could we do? And we could do a middle step here, an automation of sub-processes, to really look at which processes, especially those which are not very efficient, so where we need a lot of people, or which are not, and/or which are not safe. So if they are either, let's say, very hard work, yes, or if they are like in a big height, or with, let's say, materials which are not nice to, with regard to health, we can look at these processes. And then we can have like solutions, which I call, which are more like low-hanging fruits. So it mustn't be the 100% solution, but rather say which part of the processes can we really automate here. And here we can combine things like additive manufacturing, functional robots, extended reality, and combine it also with artificial intelligence approaches here. And how can we find these processes, and how can we find industry? So in Germany, we have a very small and medium-sized construction industry and lots of craftsmen also. And they face now that they don't have the people. So they have this lack in personnel. So they say that we can't do our projects anymore because we don't have the people. So if I provide them a solution, which is, I think, ready in 5 years, then they are not interested. But if I provide them a small solution, then they would be interested. But they say, what is automation? What is robotics? They don't know. So we set up a robotics learning factory at our institute. And we have different, it's not like a production line, but it's rather like workstations there. So we have a workstation for additive manufacturing. We have one for extended reality. We show what can be done with big data and mobile robots, and also a functional robot. This is our Carla. And people from construction industry come to our learning factory, and they get hands-on workshops. So they really work with the robot, and they teach the robot, for example, to set these bricks. And this is kind of having this learning effect, because, you know, the craftsman, you can't show just slides. He must feel it. He must get to know how it works. And this is the first part of the workshop. And the second one is that we go through the processes of the companies, of the workers there, and say which of your processes could be, with your knowledge now of these different forms of automation, could be automated. And then we create something, and then we can also provide like prototyping here and implement it at the site. And we rather look at the, let's say, Pareto principle with like 80%, and not with the robot who can do everything, but rather a collaboration then between the human workers and the robots there itself. So to give you some examples here, so this is a view of one of our workshops here at the Institute. And for example, here we have somebody working with an exoskeleton, which is automated also, and helps him to lift the things here. Then we have a platform robot, for example, which is finding its way itself. And we show just here what can be done there. And of course, we can combine. So we could have the platform robot, and we can mount on it, for example, such a functional robot. And here's a guy who is just teaching, it's not so fluently at the moment, but he's just teaching here the robot to set these bricks. And this is the I'll say experience which they are doing there. And it's fascinating for us as well, but also for our industry partners. So last slide, I want to show you. So we are planning a BIM and Robo Expo in Aachen next year, end of August. where we have some, let's say, international speakers, also like from Japan, from Korea, from Singapore, who are doing lots of things from the, let's say, from the governmental side and from the US. And we have like practical reports from the big international experts, and also an expert exhibition there. And perhaps you might be interested, then you are invited, of course, to come there to Aachen next year. So thank you very much for your attention. And I think we are both happy to answer some of your questions. Thank you.
Thank you very much for this nice talk. I would propose we have 2 chairs here. Just drag them to the stage, and I ask Kathrin to also come back on stage. And I would give the first questions to the audience. Thank you.
Oh, we get to sit.
Are there any questions from the audience? Wait.
I was wondering, this program, I think it's interesting to get craft people into technology.
Mm-hmm.
The question is, how far can you go? Is it just a teaser to show them what would be possible eventually?
Mm-hmm.
And if they are interested, what's next then?
Yes.
You know, this is a matter of education. So are people educated inside the industry? Does government have to care of it? Is it government the right player? You know, because the one we know that already exists, what we could call digital craft people, are coming, for example, from timber construction industry, but they have been formed within the industry, not outside. So what is your experience or vision for future steps there?
Well, we are working in North Rhine-Westphalia with we have these associations of craftsmen. It's called Handwerkskammer in German. And we have there 7 big Handwerkskammer, 7 organizations there. And they provide now 100 companies will come to our lab and really do these workshops with us. And the government at this time, at the state level, they are kind of financing the workshops for them. But still, we have, let's say, it's the more innovative companies, we must say. Because, of course, we have lots of craftsmen which are very reluctant with these technologies. But we have some which are really innovative. And of course, the ones who work with wood, but they are different from different perspectives there. And I think if we just try to teach them the first steps there will be also, or this is yes, I'm convinced that it works like this. So we can show them so much more and get so much more, let's say, ideas of how to automate and how to use all these digital technologies that we can really make an impact there. And then we will have like lighthouses, so really projects where we can say, okay, look, this is done. So you can, if they are doing it, you can do it themselves. So the project just started. We opened this lab this year. I'm in Aachen since 2 years, so I think, yes, we are going our steps there. And I see there's lots of interest from the very small one, from the craftsmen, but also we have lots of interest from the big ones, which have own, let's say, organizational parts where they go with digitalization. So they book the whole lab with their people, and they are, of course, a little bit more advanced in the thinking already. So regarding to your question, I think it's a combination. We need a little bit, let's say, financial support from the government, but we, of course, we need to take the people at the point where they are standing now. And I think this is one of our, at least I believe this is one of our tasks which we can do and provide from university side. Thank you.
Any more questions from the audience?
Kathrin, as you know, we love working with bricks also. I liked a lot that you deconstruct bricks and reconstruct a model while deconstructing bricks. So I think conceptually this is very nice. And I was wondering if you have been thinking about, maybe also tracking or maybe even marking the bricks with their provenience, because in a way this would mean that you could directly label while building back where a building part came from, right? Where you then could provide the model of where this building part came from with the building part. And so I think this could be interesting for the question of reuse, that you could actually know where did a piece come from exactly, even in the assembly, understanding maybe parts of its functionality, parts of its performance or use.
Thank you for the question, because we are only starting to look into this, so it's a little bit, we are also learning as we're doing. But of course, the being able to capture or measure the quality of the parts that you reclaim would be something that we are trying to look into. Of course, now we are only using vision, so there's also like some limitations to that part. And to actually also mark the parts while taking them apart. No, we have not actually thought about this, but it's actually a good idea when you think about this whole kind of tracing and tracking the materials where they are. This would be the moment when we are anyway taking it apart to also tag them at that very moment. Yeah.
I would say we can take one more question, and then I will open the Aperol. So of course you can ask more questions, but while we drink some drinks together.
Sounds good.
I have a short one. So maybe start with Kathrin. In your first project, you seem to have your own AR system solution for visualizing the environment and movements. My question is, have you tried any available solution like from HoloLens, Magic Leap, or AR Kit, for example, from iPhone or iPad, to help you with visualization and because some of them already have some spatial awareness? And if you did you have any problems with this, to using these technologies? Well, actually, maybe also goes for Professor Klemt-Albert. You showed some AR setup. Did you have any issues using this technology? How easy is it to use? Yeah, thank you.
Jogging.
So we actually used also AR Kit in that case, and also really just marker tracking. So the thing that we developed was not the spatial awareness in this case, but really just the sort of the layers of instruction on top of it. No? So, but the measuring of the environment is based on the algorithm or on the sort of API provided by AR Kit. And only in the sort of last project, what Matthias also referred to, we are looking into developing their own algorithms for this kind of spatial awareness. Yeah. And for instance, when a user has assembled a part, then it depends on the user input to say, okay, I'm done. No? So there's no automation behind recognizing which action has been performed. And we are also, there's another research going on, which I haven't been showing, but we are also looking into tracking people and recognizing not just the parts, but also the actions, which is, extremely complicated. So we are not having any useful results so far. But of course, it would be the best if, it would be the best if some autonomous system in the background would recognize not just where the objects are, but also which action have been performed automatically, not depend on any sort of clicking buttons so far. Yeah, thank you.
Mm.
Yes, well, there's really also a problem with the, let's say, how exact can we work with there. So we want to, with regard to the bridges, we want to do it without markers. And we use then, of course, GPS there. And we have, at the moment, I must admit, like 1-2 centimeters perhaps apart, which is sometimes not so problematic, but sometimes it is. So we are working now on a more exact way to do this. And yes, I think it's working out quite fine. But if you have seen very exactly at my video, there was this 2 centimeter gap. So still, it's an ongoing project. So we have the first year, I think, now at this point. But I'm quite convinced that this is working out at the end. And I think we will get a huge impact with it, because we really don't have the maintenance people. And we usually, for special problems, we need some experts there. So if we send just one guy on the site, and the others can sit in the office and tackle, of course, several of the projects and be, support from in real time, but and say, okay, look at this crack, look specifically at this, and then they can discuss what to do. I think we will very much make use of these AR technology. Yeah.
Thank you very much. Thanks to everyone joining. I want to invite you to our next and last lecturer for this seminar series, Dr. Christoph Weibel. We'll talk about powering the CD simulation optimization and machine learning. And with that, I'm closing for today. Please join us for a drink, and thanks again to both of you.